Like I mentioned last time, last time we talked about signal processing, and you already saw several examples of this kind of situation. But you have various data structures that need to be managed within the kernel, and so it's really nice to have some kind of memory allocation mechanism so that you can dynamically allocate data structures. It's just a few examples of the kind of things that people need to manage. In fact, I think that for Project 4, one of the things you have to do is set up the file descriptor abstraction like we talked about in the very first or second week. So a lot of people do that. I think the maximum number of open files is 128, if I remember correctly. You'll have to read the Project 4 details. But you just have an array of 128 entries, and then those are your file things. So you can definitely do that stuff statically, but a lot of operating system kernels do a lot of dynamically allocated things. Okay? Buffers are another one that is really important when we talk about virtual memory, and we may even talk about this in the next lecture if I remember correctly. Device interactions are interesting because with the modern PCI bus, a device can drive the bus as well as having the processor drive the bus. And a lot of times devices, they're already sitting outside of the virtual memory manager, so they don't see address translation. And so they may have a specific address range that they really need to stay within. So that's one of those things that can really affect allocations and memory layout. So anyway, but we need to have buffer space for device interactions, and so the kernel has some kind of dynamic memory allocator. Now there's two kinds of allocation, okay? And you see this illustrated really clearly in Pintos, and pretty much every operating system kernel that you ever saw the source of, you would see this. Basically, we have to have a way of getting new pages into frames for the current process, or perhaps on behalf of the kernel, for the kernel to use, so that we just get another chunk of space. So clearly this virtual address space extension mechanism is going to operate in multiples of pages. Right? So 4 kilobytes on x86 or 2 megabytes or whatever it happens to be appropriate for the hardware. I don't know how much I want to go into this in detail now, but when we have multiple level page tables, a lot of times you can actually get chunks of virtual memory in sizes corresponding to the different levels of the page table. Okay? So you see that, and you especially see that on 64-bit because we have a 4-level page table. Okay? So anyway, that's the first kind of memory allocation, but then the second kind is allocating chunks of memory for dynamic data structures. And so this basically is built on top of the virtual memory management layer. Okay? And so you'll see that in Pintos. It's like I need a virtual page. And then there's actually a little kernel allocator that just uses the page allocator to deal with those kinds of memory allocation requests. So the second kind is what we're going to talk about today, the kernel memory allocator. And if you think about it, the kernel allocator, it's really crucial for it to be a clever piece of software because everything is going to use it. And so, first of all, it has to be fast. It may be called from interrupt context. And that always complicates things because if you call malloc in your user space application, well, you may or may not block on that call. Because what if you need to malloc and there's no frame available for your process to get that piece of memory? And so the kernel may turn around and have to swap somebody else's page out. So that swap out is going to take millions of clocks, and now your process is blocked until that's finished. So you have these kinds of things that may occur during this allocation process. And because of that, we need to make sure the interrupt context doesn't block. Okay? So here's the example. Kernel allocator is called from the interrupt context. System has little available memory. And so the system needs to go and page some things out, and that will require putting the requester to sleep. This can't happen from interrupt context. So basically, kernel allocators tend to have two modes. One is give me memory or don't give me memory, but do not stop me. That's used for interrupt context. Okay, so the allocation request may fail. Of course, since most interrupts actually do need to reliably have memory to do their processing, you'll see two strategies. One is that they'll either have statically allocated memory, which is really smart. All of you might think back to your project 2 where you have a keyboard buffer. Maybe it's a circular queue. That makes it nice and straightforward. Or the OS will simply make sure that there's a pool of memory that interrupts can use that's always replenished so that interrupt handling won't have to worry about whether or not an allocation request fails. Okay? And then you have the other mode, which is that the allocation request is in process context. So it's okay to block me. It's okay to go swap out other page frames or something like that, as long as I eventually get the memory that I need. Okay? So those are the two modes you oftentimes see kernel allocators working. Okay, so those are two requirements. Has to be fast, has to handle interrupt context. Third issue is that we need to use memory efficiently. And efficient memory usage is, it's funny because this is true of all applications, but if you have a program that runs for 5 seconds and then finishes, nobody cares if you have fragmentation. So you see fragmentation kinds of issues on long-running servers, and the reality is there is no other kind of, there's no other piece of software that runs as long as the kernel does on your system. So the kernel obviously needs to be the hallmark of efficient memory use. Okay, so that's memory fragmentation. There's two kinds of memory fragmentation. Okay, you have fragmentation that is due to the code outside of the allocator, and then you have fragmentation due to the allocator itself. So those have two different names. You have external fragmentation, which is basically due to how the callers use the allocator in context or in concert with how the allocator makes choices. So that's external fragmentation. And this is the example that we give a lot in CS24 is you have 1 kilobyte, then 2 kilobytes, then 1, then 2. And then the two 1 kilobyte blocks are freed, and then somebody asks for a 2 kilobyte block. And although you do have 2 kilobytes available in the memory pool, it's not contiguous, so the allocation request fails. Okay? So that's an example of external fragmentation. Internal fragmentation, so that is basically what the allocator imposes on other pieces of code. And so this is where internal fragmentation can be really nasty. Let's say that the allocator rounds all requests up to 1 kilobyte in size. Okay, that seems wasteful, especially when you see these requests. So you get like a 750 byte request, and you can see that we waste 274 bytes because we round that up. We allocate 1,800 bytes, well, we round that up to 2,048, so we waste another 248 bytes, another allocation request, and then another one. And you can see 1320 is just enough over 1,024 that we got to allocate 2 blocks. And so you can see that with this kind of an approach where we always round allocation requests to a particular size, we easily incur a lot of overhead. We waste quite a bit of resources with this kind of a strategy. Okay? So that's internal fragmentation. So internal is inside the allocator. It's poor choices, let's say. And then you have external fragmentation, which is really more of an interplay between code using the allocator and perhaps choices the allocator makes. But a lot of times it's always possible to figure out ways of wasting memory regardless of the allocator strategies. Okay, so those are internal and external fragmentation. Now, like I was saying before, you do run into situations where the kernel needs more memory for its own address space. Again, talking 32-bit, it'll have a 1 gig virtual address space, and it may or may not have physical pages allocated or physical frames allocated to that entire 1 gig address space. Probably not, given most operating systems don't want to have quite that much overhead. So that's on 32-bit. On 64-bit, you've got like 64 terabytes or something for the address space. So of course it's not going to all be allocated. But, so it'll need more memory. It'll allocate more virtual pages to its own address space. So this is a pretty common scenario where you try to satisfy an allocation request. Again, this is the kernel allocator, and there's not enough free space, so it turns around and asks for pages from the page allocator. Okay? And so basically, since we have this interaction here, you can imagine that you'd like to make the most of every page you actually get. So again, you're not wasting a lot of resources for the entire system. Otherwise, you incur a lot of swapping, the system runs slowly, and everybody's sad, right? People won't want to use the software. Okay? So in general, what you notice is that the best kernel allocators are highly tuned to work efficiently with the virtual memory system. Okay, so that's another common theme you see in the way that these kernel allocators work. Okay. Now, there are certain patterns that you notice. It's great because when you have an OS kernel like Linux, or you have Minix, or you have BSD, or you have Mach, or any of these kinds of things, you can always actually trace what the allocation requests are like. And so you can say, what are the common memory usage patterns that should inform the design of a kernel allocator? Okay, so that we can design the allocator to do that well. So normally there's a maximum size. It tends to be that a lot of the data structures inside the kernel are relatively small, so they don't need to be allocated. You may have them allocated and released frequently, but it tends to be the allocation requests are small. Less frequently, you have larger buffers that are allocated. So maybe a 4 kilobyte buffer, maybe an 8 kilobyte buffer, but those tend to be a lot less common. Okay? You tend to have a lot of requests for a particular size, because there's a certain kind of thing that you're allocating a lot. Think about semaphores, if you were to dynamically allocate semaphores, or other kinds of locks for synchronization inside your kernel. Let's imagine you have, what are they called? Signal descriptors being allocated inside of a process because it's sending and receiving signals. So that's another great example where you'd have that kind of thing happening all the time. Okay, so there is a pattern that you see frequently called allocate, free, reallocate. And the idea is I need this data structure temporarily for a short period of time to carry out some work. I use it, then I release it. But then I need another one of the same size shortly thereafter. And so you end up with this pattern, allocate, free, reallocate. So basically, we want to take this into account in our design. And you'll notice that the most powerful, most commonly used kernel allocators are designed around this concept. They're really good at handling this kind of circumstance. Okay? All right, so given all of that, we'll talk with the simplest allocator. And so what we're going to do is cover probably 6 or 7 different kinds of allocators in the next 2 lectures. And I want you to think about these characteristics that we've already talked about, because you'll notice that they start out really dumb. Like the resource map allocator or the explicit free list allocator is what most students implement for CS24, the assignment 3, where they have to implement a memory allocator. Okay? They build basically this thing. And I know that basically no one in CS24 thinks about virtual memory page sizes, because people don't really know about virtual memory at that point. Okay? So basically this is just keeping track of where does the block start and how large is it. That's basically all we keep track of. We obviously have non-overlapping regions, because it would be terrible to have overlapping memory regions. That would be highly bug-riddled code. But anyway, we just keep some kind of collection of these pairs of starting address and size so that we can figure out when we can allocate more memory and where it should come from. So yeah, if this list is maintained in order of increasing base address, it's really easy to coalesce adjacent regions. That is obviously a benefit. Also, if we have the list maintained in increasing size, it becomes easy to find a block the size that we need. Okay? So we have obvious trade-offs here, and so while this is very simple, you can see that it's really difficult to tune this for being good at multiple things at once. We can either make it easy to coalesce and hard to find things of a particular size, or vice versa. So simple to implement, almost no internal fragmentation. I mean, you might have a little header on these things, but that's about it. You can implement various placement policies as well. One of the things we don't really talk about in CS24 is that regardless of the placement policy, you can come up with an allocation sequence that makes it behave really badly. So I wouldn't want you necessarily to look at this and think one policy is better than another. There may be better or worse policies in specific usage scenarios, but in general, you can figure out a way to gum up any of these. And there's various improvements you can make on this allocation mechanism, which we talk about quite a few of those in CS24, so I'm not going to really talk about that very much. Okay, drawbacks, very prone to external fragmentation. Okay. So internal fragmentation, we waste very little space with this, but external fragmentation can become a real problem because, again, it's hard to pick a placement policy that plays well just with general allocation request sequences. You can almost always come up with a sequence that makes things worse. And so this is a problem that the kernel can run into. One of the things I'll mention as an aside, again, probably none of you have experience with this just because of how young you are. You live and program in a world that is a lot better than it was 20, 30 years ago, I have to say. But if you take Windows before Windows 95 or Mac OS before OS X, a lot of these kernels would actually hand out representations of data structures using handles as opposed to pointers. And the reason why they would use handles is because, or I should say one reason, there were a number of reasons, but one was because if you have a handle that's opaque, it doesn't correspond to an address, and the kernel can then map that handle to an address. And that would allow the kernel allocator to coalesce memory periodically, so it could actually move things in its kernel memory because you just have a handle. And as long as it has a table that says this handle corresponds to this data structure starting at this address, then the handle doesn't change and the kernel could deal with fragmentation issues more easily. Okay? So that was a thing that you would see in older OSs because of fragmentation being an issue. Okay, this is slower than other kernel allocators. I mean, you will have to take my word for it because I'm just going to tell you for now that there's much faster ways to do things. But it turns out that you can make allocation and deallocation quite speedy, and this is a slow approach. Okay? This resource map allocator also doesn't care about virtual memory. So it doesn't say, hey, am I actually utilizing virtual pages efficiently, maximally? So you can imagine that this might be your first cut to get an OS working, and I think that the Pintos kernel allocator is something like this. Because again, Pintos runs for, worst case, like 5 minutes, and then it times out and is killed. That's about the length of time that Pintos runs. But a real OS would never use an allocator like this for very long. Power of 2 free list allocators. So basically, these are designed to optimize allocation performance. Okay? So power of 2 free list allocator. Basically, another aspect of this is if you happen to use more than a whole page, then it might be rounded up to the next whole page size. So that might be an option. And this allows you to maintain a whole collection of free lists corresponding to various allocation request sizes. So notice here we start with 32-byte blocks, and we have a list of available chunks of memory at each one of these sizes. 64-byte, 128-byte, all the way up. Now, that's nice. Allocation becomes really fast. We can just figure out what is, what list corresponds to the allocation request size, and we can just grab one out. Okay. So that's nice. Freeing can be fast as long as somehow we remember what free list the block came from. Or, in other words, what size the block is supposed to be so that we can dump it back into the appropriate list. And this is where it starts to get a little bit challenging, because how are we supposed to remember the size of a block? Well, the only real option that we have so far, at least in using the infrastructure we've discussed, is you have to take a little bit of that block and devote it to using, storing the size or storing the free list that it came from. Okay? So that's the issue. Let's say we have this little block right there just floating in space, and so that was previously allocated, and then it's released, and somehow we have to get back to what is the block's size. Okay? So we could use a word if we we want to be really wasteful, but we kind of are constrained to do that anyway because we want to make sure that whatever we hand out is going to be word aligned, be efficient for programs to use. And so let's say that we allocate a word of it to store the free list that the block was from. So we know that this is a 128-byte block because that's what the pointer says. Now I realize here that there's something you wouldn't put that word at the end because you don't know where the block ends, so you would probably need to have it be the first word saying, hey, this is a 128-byte block, and so you know where to stick it. Okay. And see, the issue that we have with this is we have a power of 2 block size. It turns out that programmers love using power of 2 block sizes because hardware loves power of 2 block sizes. And so if you take a power of 2 block size and you throw away one word from it, now you're going to start running amok with the common allocation requests, which are a power of 2, and then you say, well, I really only have space for a power of 2 minus 1 word, so I've got to double the size, and so I'm wasting a ton of space now. Okay? And so like I say here, 50% of the block space would be lost. And there's research showing that in these kinds of power of 2 memory allocators, they lose a ton of space based on this behavior of programmers, which is to generally allocate power of 2 sizes. Okay? So that's bad. We don't like that at all. Now, what happens when we have a request and there's no block of the available size? This is an upside of the power of 2 free list allocator. Okay? So like I say here, we have a request for 48 bytes. So we know 48 bytes is going to fit inside of a 64-byte block, even if we waste a word of it on remembering what free list the block was from. But we don't have any 64-byte blocks. So what we can do is we can take the next largest size block that we have available and split it into a number of smaller blocks. Okay, so in this case, we might take a 256-byte block, split it into a 128-byte block, and 2 64-byte blocks. Okay, then we propagate those to the appropriate free lists. And again, this is nice and simple. This is going to be a fast operation to perform. And let's see. Yeah, the issue here is that when you do this kind of splitting, you don't know where these things live relative to each other, and so coalescing starts to become more difficult. Okay. There are options for solving this problem. Okay. One, you could do something really slow and just traverse the entire thing and try to figure out who can be coalesced. You can try to do a boundary tags approach like Don Knuth suggests in his one of his papers. You could say, well, I'm going to put a header and a footer so that when I have a block, I can just back up and see what size the previous block is and whether or not it's available. And that would make coalescing fast. But when you use boundary tags, then you're losing even more of the block. So internal fragmentation starts to become more and more of an issue with that. Okay. So this is the challenge. This is fast for allocation, but coalescing is really difficult with this approach. There's internal fragmentation issues, and I would say there's internal and external fragmentation issues because remember that if you can't really coalesce well and your placement strategy isn't very clean, then you could end up with a lot of available chunks of memory just spread, sprinkled throughout your kernel memory space. So that's not great. Okay. But you can see how it is slightly more sophisticated. Okay. So benefits, very fast allocation and deallocation. Remember deallocation, we can just go back to the free list that it was in. Okay. Good at reusing previous allocations of the same size. So allocate, free, reallocate is actually going to be fast here. I say this is resilient against external fragmentation. As long as you have a way of reclaiming things efficiently, then this is true. Okay, so you would have if you were building this, you would almost be absolutely constrained to use boundary tag approach so that you could make coalescing fast, because you really would need to do that to deal with external fragmentation. Okay. Drawbacks. So internal fragment. Yeah, this is the research. that I wanted to mention briefly. I didn't have it on the slide where I introduced the issue. But internal fragmentation, remember, because you're going to have power of 2 minus epsilon as your actual available space in the block, because you have to remember where the block came from, and so forth. You waste a lot of space on that. Okay? So no good. All right? Yeah, and so coalescing, like I said, you have to do something for coalescing so that you can actually be resilient to external fragmentation. Okay, so that's power of 2 free lists. Now, here's another interesting option. Let's say that somebody needs this 48-byte allocation, and so you say, all right, I'll try to find a 64-byte allocation, and I only have 256 bytes and up. Well, another option is to take an entire page and split the entire page into blocks of the same size. Now, we're talking powers of 2, so we know that as long as the request size is less than the page size, well, I'm going to be able to pack more than one of these things in there, and that might be pretty nice. Now, a subsequent thought is, if I'm splitting the entire page, maybe I can start keeping track of the details at a page level as opposed to at a block level. Everybody see that? So instead of saying each block needs to know what size it is, the entire page, I can keep track of the size of everything in the page. Okay? So 48-byte request, new 4-kilobyte virtual page, split it into a whole bunch of 64-byte blocks. Okay? That's really nice. And so now we can start thinking about keeping track of details at the page level rather than at the block level. So you can see that we're starting to get a certain sense of building a kernel allocator around the virtual memory system. Okay? So we're going to start managing things at a virtual page level. This is basically the basis of the McKusick-Karels Allocator, and this allocator is one that I would not mind using in an OS. It's a pretty decent approach. Okay? It's a variant of power of 2 allocators, but it uses information, or it manages information at the page level rather than at the block level. So this made an appearance in an earlier Unix kernel. 4.3 BSD is pretty old at this point. But basically, the obvious benefit is now power of 2 blocks are really a power of 2, because I actually use some other information to keep track of what size is a block when it needs to be released. Okay? Now, like I say here, the kernel allocator maintains an array of details for every page in the allocation pool. And again, that might seem wasteful, but if you can pack the details into a byte per page, then suddenly that isn't so expensive. Even if you have like a 4-kilobyte block, well, a 4-kilobyte block can describe 4K pages, and so now you're talking what, like 16 megabytes you could describe in one 4K page as far as the page sizes and so forth. 16 megabytes ain't too shabby. And if you need 2, then that's 32 megabytes. So I mean, this is really pretty efficient. Okay. So basically, the array entries would say either the allocation block size, okay, or they would say this block is available, or they would say that a block is actually part of a previous block allocation, so that you may have a run of multiple blocks or multiple pages if you need an allocation that's larger than one page. And just as a little detail, if you were trying to think of how to do the allocation block size in a byte as opposed to in a Word or something like that, so that you can keep this description smaller, you could just represent the block size as an n that's actually like 2 to the n. So you could just use that, like what power would you raise 2 to figure out the actual block size. And that's nice and efficient. So we're still taking advantage of the fact that this is power of 2. Okay? So here's the example from the McKusick-Karels paper. That was for a machine with 1 kilobyte pages. And so you would have a description something like this. The first page is 1024 byte allocation. The next one is 256 byte allocations. to 512 byte allocations. You can see now we have a run of pages because we have an allocation that is up to 3072 bytes. So you have continued, continued, and so forth. So it becomes relatively straightforward to manage the information for this allocator. Now here's the thing. Let's say that somebody wants to free a block. Allocation should be, no problem. We should be able to just go ahead and keep track of that. But let's say that somebody wants to free a block. So they give you back a pointer. And now you have to figure out what's the block size corresponding to this pointer. Well, it's straightforward. You just take that pointer and you round it down to the page size. Okay? And then you use that to look up in the descriptive array saying, okay, what is that page's allocation size? Now you know the allocation size and you know exactly what to do. Okay? So this is pretty nice. And really we should say address divided by page size. We should probably say address minus the pool start. That's always something that's funny because it leaves everybody tends to leave that out of the discussion. But this pool is going to start at some non-zero address. So it would be the address minus the pool size divided by the page size. That gives you an index into the array describing the sizes of things. Okay? Make sense? Cool. So yeah, block address 74. Oh, hello. Address 7424. Page size 1024. Well, you take 7424 and our start is 0, so that makes it easy. You divide that by 1024 and you get 7, which is probably difficult to guess since we're working with 1024. And you look that up and it says this is 128 byte blocks. Okay? Now you can obviously store other things as well. Like if you have a minimum allocation size, you might have a bit vector for each page saying which blocks are available and which are not, and so forth. Okay? There's a number of ways that you can do this stuff. You could also have the starting pointer to a first free block in the page and then have all the free blocks chained together. So there's a number of ways you could construct this to make it easy to allocate pages allocate requests and free them quickly as well. Okay, so that is some information about McKusick-Karels. Like I said, it is better than a power of 2 allocator. The main issue here is that power of 2 allocation requests still waste a lot of space. That's the thing. If I have 40 byte allocations all the time, like let's say that my signal description structs are not that big and they're 40 bytes or something like that, I'm wasting a lot of space every time I make an allocation request because now I'm using 64 bytes to represent a struct that only requires 40 bytes. Okay? So that's not great. Now, we're not going to actually solve that problem until next time. I'm just going to be really upfront with you and say that we're not going to solve that problem until next time. But we are going to talk about one more kind of allocator that's pretty, it's fun. I really like buddy allocators. Plus, they have kind of a cute name, buddy allocators. But buddy allocators basically also handle power of 2 allocation requests. Okay, so you get an allocation request of a certain amount and it'll round it up to the nearest power of 2. There's various other kinds of buddy allocators as well, which you can read about if you're interested, but I'm not going to talk about them today. Basically, each block has a size associated with it. That part is not of any surprise, but it's represented by a size order. Okay? And so you might have a minimum block size, and that's definitely not going to be 1 byte. So maybe it's 32 bytes or it's 64 bytes, and that's considered to be size order 0. Okay? And that's a power of 2. And then any block of order I, where I is 0 or more, is going to be the size of the 0 order block times 2 to the order. Okay? So a block of order I has size order 0 block size times 2 to the I. And so if we had blocks that were 32 bytes, then order 0 blocks are 32 bytes, order 1 blocks are 64 bytes, order 2 blocks are 128 bytes, and so forth. Okay. Really straightforward. Okay, so size order is basically like just a way of referring to a block size and from relative to some base size that's a power of 2. Okay, so we maintain a free list for each block size. 32 byte blocks or order 0 blocks, order 1 blocks, 64 bytes, and so forth. Okay, so initially you start out with the entire pool being 1 block of the maximum size order that will fit. Okay, so whatever that maximum size order is going to be based on the pool size. So this is just a simple example. If you have 1 megabyte, or technically that's 1 megabyte if you understand that term. So we have 1 megabyte of memory. The order 0 block size is 32 bytes. So it's just how many 32 byte blocks can I fit into 1 meg? And you would see that the maximum order that you can possibly fit in is 15. Okay, so 2 to the 15 times 2 to the 5 is going to give you 2 to the 20. When you have a block, you can split it into 2 blocks of the next smaller size order. Again, not a surprise. So if we have 1 block of size order 15, we can break it into 2 blocks of size order 14. One of those could be broken into 2 blocks of size order 13, and so forth. Okay? And the important detail is when you have a block and you break it into 2 blocks, they're adjacent, they're buddies. Okay? And that's an important detail. Even though you may have 2 blocks that are adjacent, unless they came from the same parent block, they're not buddies. Okay? And basically all breaking apart and coalescing works with your buddy block. Okay? So a free block of a given order can be coalesced with its buddy if the buddy is also free and the same size order. And then you get a new block that's size order I plus 1. And so this constraint, again, this is a placement constraint, and it's pretty restricting. In fact, in CS24, I built a buddy allocator just for fun, a binary buddy allocator, and ran it against the test suite just to see how it would do. And it had the worst memory utilization I had ever seen. And it's because of these constraints. It just makes it really difficult to use memory efficiently when you have this kind of placement constraint. Okay, so allocation request is made. It's round up to the nearest power of 2 with a floor of the order 0 block size. Obviously, if it's smaller than that, it's got to be brought up to the size order 0. And then the allocator computes the size order of the block. It's not difficult. Okay. And then you figure out if there's a free block. If there is, you just pull it out of the free list, and out it goes, out the door it goes. Otherwise, what you do is you find the highest size, the next highest size that actually has an available free block. Okay? So like I say here, the required size order is A, so that's the one that we need. We have the smallest available size order is B, and we know that B is greater than A because there's no block of size order A yet. Okay? So while B is larger than A, we take a free block from B, we split it into 2 buddy blocks that are now size order B minus 1, and we decrease B by 1. Okay? So we might take a big block, split it into 2 small ones, and then we take one of them and split it again, and then we take one of those and split it again, until we end up with blocks that are the size that we need, A. Okay? And then we're done. Okay? So, here's the example. So we have not a size order 15, because that would be way too much effort. But we have order 0 block size of 32 bytes, max order of 3. So what does that mean? We can do, so 32 times 4 is 128 bytes in this pool, is all we have. So allocate a 20 byte block. Well, we round up to 32 bytes. There's definitely no 32 byte block. So we split the order 3 block into 2 order 2 blocks. And we do that again. We split the order 2 block into 2 order 1 blocks. We take the order 1 block and we split it into 2 order 0 blocks. So now we finally have space. Yeah, so I guess this is a 256 byte pool, isn't it? Not a 128 byte pool. Okay, so now we can say we have a block that is in use for this allocation request. So if we allocate another 40 byte block, we round it up to 64 bytes. And notice now, well, we had a block that size, so we go ahead and satisfy the request. A 60 byte block, well, we don't have a 64 byte block available, so we have to split the second 128 byte block to get a block of the appropriate size. Okay, everybody see that? So it's pretty straightforward, conceptually. If you're in CS124 at this point, you have more than enough skill to implement this. It probably would be a fun, relaxing thing to do. Okay, so when you free a block, the block has to be marked free, added to the corresponding free list. That's all pretty obvious. But then what you need to do is this coalescing mechanism. So you start with the current block, and as long as you haven't hit to the largest block size, basically you look for the block's buddy. Okay? You check to see if the block's buddy is the same size order as the current block. If it is, then you can look to see if it's free. And if both of these things are true, then you can coalesce the current block and its buddy back into a new free block that's the next highest size order. And then you can repeat that process until the allocator has reclaimed as much memory as possible. Okay? So blocks may only be coalesced with their buddies. So if we had this, and notice we actually have 3 order 1 blocks allocated now, so 3 64 byte blocks allocated. We free the first order 1 block. Now what happens? The allocator says, okay, this is supposed to be the buddy of this block. Not the right size order, and it's not free. Definitely cannot coalesce, so we end up with just this. Okay? So the allocator would stop. Now, some point in the future, the kernel says, I'd like to free the second order 1 block. Okay? And again, this block's buddy is over here, not over here, because these two came from the same parent. So even though, yes, it's the same size order, it's not free, so no coalescing can occur. So this is what the pool looks like now. We free the first order 0 block, and this is going to be fun, right? So we free this guy. Its buddy is right here, because they both came from this block. And once it's free, we can combine them into a block of the next size order. Okay? So we get this. Again, so if we had this block, and we combine this block into it, then now we have this block, and we're trying to see if we can combine it. So again, this block's buddy is this block. We can combine them. They're the same size order, and they're both free. So we end up with this. And then that's as far as we can go. Are there any questions about this mechanism? Yes?
So you have to keep track of the block sizes somehow.
You do need to keep track of block sizes somehow.
Yeah, how's that done?
So yeah, I actually talk about it in a subsequent slide. I mean, it's a good question. How do you keep track of the block sizes here? Since you have some minimum block size that you allocate, you can again rely on a similar strategy to the McKusick-Karels Allocator, where you keep a separate array, and that array has an entry at sort of the minimum size order that can be maintained in the pool, so that you'll have those entries, and those are where you keep track of the size orders. Yeah. A bit wasteful. So you can see how this has overhead as well. I'm showing you like the prettiest parts of it, and even the prettiest parts aren't that pretty. So, but I'll talk about that in a second, because even though buddy allocators are fun name, kind of a slow implementation, they actually get used rather frequently, and I'll explain where and why momentarily. Any other questions at this point? Okay, so this is the thing that's really interesting about buddy allocators. Okay? Notice I have offsets from the start of the pool. There's a really easy trick to find a block's buddy, because the block's buddy tends to be at an offset with just 1 bit flipped as compared to the other buddy in the pair. Okay? So You XOR the block's offset from the start of the memory pool with the block size, and that gives you the buddy address. So it becomes really easy to look up who your buddy is. Okay, so buddy of the second order 0 block. Okay. So that would be the block starting at offset 96. Okay. So you have that bit pattern is 96. You exclusive OR it with the size of 32 bytes. Remember that we require that order 0 block size is still a power of 2. This is part of the reason why, so that we can still do this. Okay, so we exclusive OR it with the size, and we end up with 01000000, which is 64. Okay, so you can see how buddies differ by 1 bit. That's the special thing about this mechanism, which basically means the tree structure that's maintained by this allocator is easy to compute, which means we don't have to store it. We don't waste space in blocks keeping track of who's related to whom. And so you get a benefit and a drawback from that. You have this weird, massive increase of internal fragmentation because of the placement policies. But it becomes really easy. You can use the entire block because you can just compute where the block's buddy is. So yeah, like I said, each bit in a block's offset from the start of memory pool indicates whether it's the left or right buddy at each level. Okay. Again, basing this from a 0 starting point. Okay. So offset 96, topmost 0, says I'm in the left half of the order 3 block. Second 1 bit says I'm in the right half of the order 2 block. Third 1 bit is in the right half of the order 1 block. Okay. Left, right, right. Pretty cool. I love that part. It's kind of neat. Okay. So, as was noted, you do need to keep track of some details for each block. And so, a lot of times what people will do is maintain a separate array of this information. Okay? Since size orders tend to be relatively small, you can do it in a byte, you can do it in 2 bytes, something like that per block, and that allows you to keep track of this stuff. But of course, you have to maintain that array at the minimum size order. So for something like this, 256 bytes, and the smallest size order is 32, well, that means that I have to keep track of 8 entries, regardless of whether I'm actually, whether or not I have 8 allocated chunks of memory. Okay? Not great, but not the end of the world, especially given how they're used. Okay, so they are fast, they're nice. Coalescing, pretty fast. Particularly when it comes to recoalescing and releasing virtual pages. That's one of the things that's really nice. If you want to figure out if an entire virtual page is reclaimable, well, if the free block sizes have grown up to the appropriate size order where it's a full page, now you know that full page can be released back into the page pool. So that's one of the things that's really nice about this. Internal fragmentation, still terrible. So here's how people often use them. They will use buddy allocators for managing pages, whole pages. They won't actually use them on smaller smaller allocations below a page size. Or maybe they'll use them for 4 pages or things like that. And so that way, obviously, if your minimum allocation size or your size, your order 0 page, or sorry, let me say this correctly. Your order 0 allocation size is 1 or more pages, then that makes it so you have to keep a lot less information around. Okay? And so, for example, sometimes you'll see a buddy allocator used to manage runs of pages in the page pool, and then internally within pages, you'll have some other allocator utilized. Okay? That tends to be the common approach. Any questions about this? So that's the first part. Let me tell you the last part. Okay. So here's the thing. Remember that our common pattern is allocate, release, reallocate, same size. And so if we have this allocate, we break things down, release, we coalesce things back up, and then reallocate, you break things back down again, that's a freaking waste of time. Okay? So we don't want to continually coalesce over time. And so it tends to be that you have another dimension that you can consider buddy allocators. Do they coalesce eagerly or do they coalesce lazily? And it tends to be that in these kinds of usages, you want lazy coalescing, not eager coalescing. So you don't coalesce all the time. You're not spending that time all the time. So, yeah, deferred coalescing sounds a little bit better, I suppose, than lazy coalescing. But basically what you could do is say, hey, do I have a lot of small free blocks? Would it make sense to see if I really need to reclaim some of this, aggregate it into larger chunks? Another option, of course, would be, hey, do I need to reclaim page frames? And are there maybe some frames that are available if we coalesce? So you can imagine how coalescing can be done at sort of checkpoints where it would make sense to do so. Okay. So again, any questions about this? All right. So what I will say is next time we will talk about the cool modern ways that kernels allocate memory that do really well and have very low internal and external fragmentation. So they actually solve these problems really efficiently, and they're kind of the wave of the present because they're just so dang good. So I'll see you all next time. We'll talk about that.